Hello. In this video, we're going to look at the derivatives of inverse trig functions. Now that we've spent some time getting familiar with the trig functions, we want to find their derivatives. For example, what's the derivative of sine inverse of x? Well, perhaps it's cos inverse of x. That seems reasonable based on the previous trig functions, but how could we be sure? Well, we would need a proof. We'd need some type of argument. And so let's try y equals sine inverse of x. Like solving a regular sine inverse question, we're going to take sine of both sides, giving us sine of y equals x, which I'm going to write as x over 1, so I can draw myself a little triangle. Over here, we're going to have y. Sine, we know, is opposite over hypotenuse, and so we're going to be left with a missing side. Again, we can use a little bit of Pythagoras here, right? This missing side is going to be question mark squared plus x squared equals 1 squared. So if we move it over, question mark squared would be 1 minus x squared, and we get square rooted, so the missing side is the square root of 1 minus x squared. So we'll put that in on the missing side. Now, well, okay, we have a little triangle, we solved our missing side, but what do we do with that information? The thing is, because we took sine of both sides, we now have an equation right here. Sine of y equals x. And because there's no longer a sine inverse, we can actually take the derivative of this. The only technicality, of course, is that when we do the derivative, we have to use implicit, because it's not going to be just a simple y equals. The derivative of sine, we know, is going to be cos. And then we have to use the chain rule, dy dx, using implicit differentiation. On the right-hand side, we have the derivative of x, which is simply 1. We go ahead and rearrange for dy dx, and dy dx would be equal to 1 over cos of y, which, if you think about it, is the same thing as secant y. And looking at our triangle over here, either thinking about it as 1 over cos of y or secant y. In either way, we're going to be looking at the hypotenuse and the adjacent. Cos of y would be adjacent over hypotenuse. Secant is going to be hypotenuse over adjacent. And so we write that down. We have hypotenuse of 1 over adjacent of root 1 minus x squared. And so therefore, the derivative of sine inverse of x is equal to 1 over the square root of 1 minus x squared, which is actually a little bit shocking because we thought it was going to be cos inverse, and it turns out not at all. The derivative of sine inverse x is not cos inverse of x. It's 1 over the square root of 1 minus x squared. Interesting. It appears we get that type of algebraic expression, not a trigonometric expression at all. I wonder what happens for the other inverse trig functions. Now, before we do the derivative of cos inverse, take a guess. Do you think it's going to be negative sine inverse of x? Do you think maybe there's going to be some roots and some squares? Do you think it's negative because it starts with c, or do you think that rule doesn't hold anymore? Take an educated guess on what you think the derivative will be, and then let's go ahead and do the proof. So we're going to let y equals cos inverse of x. Take cos of both sides. Cos of y equals x, which is equal to, of course, x over 1. Go ahead and draw yourself a little triangle. Cos is adjacent over hypotenuse. Adjacent over hypotenuse. And the missing side will be square root 1 minus x squared, again using Pythagoras. Pop back over to our equation. We take the derivative and get negative sine y dy dx equals 1. Isolating, we get dy dx is equal to 1 over negative sine y, which we could write as negative cosecant y. Now looking back at our triangle, either thinking about it as the reciprocal of sine or thinking about it as cosecant, either way we're going to be looking at the hypotenuse and the opposite, because sine is opposite over hypotenuse. Cosecant is hypotenuse over opposite, giving us our final answer of negative 1 over root 1 minus x squared. And so it turns out the derivative of cos inverse of x is not equal to negative sine inverse. It's actually equal to negative 1 over the square root of 1 minus x squared. So we'll put that up here for our second rule, negative 1 over the square root of 1 minus x squared. And maybe you suspected the negative. I guess it kind of makes sense because cos has a negative, so maybe cos inverse also has a negative. But it's weird that we get this root again. It seems to be maybe typical of these inverse trig functions, that we don't end up with trig functions for their derivatives. We end up with some type of radical with some type of fraction. Now, what do you think the derivative of tan inverse might be? Again, take a guess. Even if it's a shot in the dark, write something down. It's better than nothing. And then let's go ahead and try to find the derivative. So we're going to let y equal tan inverse of x. Take tan of both sides, and tan y equals x, which is the same thing as x over 1. And we're going to draw ourselves a little triangle. Tan we know is opposite over adjacent, so we get x over 1. And the other side is going to be the square root of 1 plus x squared, using Pythagoras. Now we pop back and do the chain rule. Secant squared y is the derivative of tan, multiplied by dy dx equals 1. Solving for dy dx gives dy dx equals 1 over secant squared y, which is going to be cos squared y. Well, looking at our triangle, cos is adjacent over hypotenuse. So this is going to be adjacent over hypotenuse, 1 over 1 plus x squared, all squared, or 1 over 1 plus x squared. And so it turns out that the derivative of tan inverse of x is 1 over 1 plus x squared. Again, perhaps a surprising result for you. The derivative is 1 over 1 plus x squared. Now, what do you think the derivative of cotan inverse would be? I mean, following the same pattern as sine and cos, if sine and cos are related but just with the negative, it would seem reasonable that the derivative of cotan would be related to the derivative of tan, 1 over 1 plus x squared. But because it starts with a c, you'd simply introduce a negative. And that is indeed the derivative. Please make sure you fill in the proof for homework. Now we'll do the derivative of secant inverse together. Again, you could take a guess at this one, but it's a little bit complicated. Secant tends to be more complicated, both for its derivative and for its inverse derivative, but the process is the same. We let y equals to secant inverse of x. Then you get secant of y equals x, which is the same thing as x over 1. Go ahead and draw yourself a little triangle. Secant is going to be equal to, well, secant is 1 over cosine. So cosine is adjacent over hypotenuse, so this must be hypotenuse of x over adjacent of 1. Solving for the missing side gives you x squared minus 1. Now we're going to go ahead and take the derivative. So the derivative of secant is going to be equal to secant y tan y dy dx. Derivative of x is 1. Isolating for dy dx, we get 1 over secant y tan y, which gives you cos y cotan y. Now cos y is adjacent over hypotenuse, so that's going to be 1 over x. Cotan is going to be the reciprocal of tan, so if tan is opposite and adjacent, it'll be adjacent over opposite. And so simplifying that, we have the following. The derivative of secant inverse of x is equal to 1 over x square root x squared minus 1. So we can put that up in our rule. 1 over x square root x squared minus 1. Finally, we have the derivative of cosecant inverse, which, you guessed it, is just the negative of secant inverse. So negative 1 over x square root x squared minus 1. Please complete the proof for homework. Now let's try to apply these rules to some basic derivative problems. Let's say we have the derivative of sine inverse of x. Well, that's just a memory question. We need to have the derivative memorized as 1 over the square root 1 minus x squared. What if we had the derivative of sine inverse of x squared? Oh, this is going to be a little trickier. We go to do the derivative as 1 over square root 1 minus. But what do we put here? Do we put x squared? Well, no, the rule says we're supposed to put just x squared, but x is whatever the inside function is. So we actually put x squared and then multiply by 2x with the chain rule. One way to think about it is that the derivative of sine inverse of a blank box is equal to, well, it's 1 over the square root of 1 minus that box squared times the derivative of the box. You really want to pay attention, because if the thing on the inside is anything other than an x, that whole inside function needs to be rewritten and then written with the chain rule beside it. Now don't look at your notes and try to answer the following multiple choice question. Which rule is incorrect? Is it A, B, C, or D? Take a moment and think about it. Okay, well, let's go through these one at a time. The derivative of arcsine, which is sine inverse, that definitely is 1 over root 1 minus x squared. So that rule is correct. Arc cos, that's cos inverse. Yep, that's correct. It's just the negative of the sine. Arctan and arccotan, these look a little strange. Well, we could pull the negative out of this one and make it negative 1 over 1 plus x squared. So that would actually be correct. But arctan x is supposed to be 1 over 1 plus x squared. And so this rule is incorrect. The answer is C. Let's go ahead and try some more complicated inverse trig problems. Here we have the derivative of cosine inverse of 2x squared plus pi over x. Well, using our rule, we're going to have negative 1 over the square root of 1 minus that whole inside, 2x squared plus pi over x squared, times, well, the derivative of 2x squared will be 4x. And this we should probably write as pi x to the minus 1. So that'll be subtract pi x to the minus 2. Using, of course, the chain rule here when we do the derivative. Let's try this one. Secant inverse of cos of 2x. All right, well, there's more chain rule to be had here. We do 1 over. The derivative of secant inverse is going to be x, square root x squared minus 1. But our x is not just an x. Our x is actually cos 2x. So it's cos 2x, square root, cos 2x squared minus 1, times, well, the derivative of cos is negative sine 2x, and then times a final 2. Let's try a tan inverse question. The derivative of tan inverse of secant of x cubed. Well, this one's a real doozy. We go ahead and do tan, which is 1 over 1 plus x squared. So 1 over 1 plus secant of x cubed squared. Then we multiply. Derivative of secant we know is secant tan. So we get secant x cubed tan x cubed multiplied by 3x squared. And we're done. Let's go ahead and try everyone's favorite, the product rule. We have the derivative of cosecant 3x times cosecant inverse of 5x. Well, the derivative of the first one is negative cosecant 3x cotan 3x times 3. Then we leave the second one all alone. Cosecant inverse of 5x. If you want, you can put each one of these in square brackets just to help you see the product rule happening. Plus, rewrite that first one, cosecant of 3x times, well, cosecant inverse is going to be negative 1 over 5x square root 5x squared minus 1 times 5. Again, if you want, you can put each one of these in brackets to help really show you the product rule. Okay, what else do we have here? Looks like a quotient rule. I knew you were waiting to do a quotient rule question. You just couldn't help yourself. Well, here it is, our favorite quotient rule question. Let's do low, so cosecant inverse, x squared plus 5x squared. Let's put that in some brackets. D high. Tan inverse is going to be 1 over 1 plus x squared plus 2, all squared, times 2x. So that's our low d high. Less, now we're going to need high d low. High, tan inverse, x squared plus 2. D low, negative 1 over x squared square root x squared squared minus 1 times 2x. That's the derivative of the cosecant part. And then we have to put plus 10x all over the denominator, cosecant inverse, x squared plus 5x squared, squared we go. Again, a little bit crazy, but as long as you sing the song, you should be able to get the correct answer. So we have one more to go here. We're going to do a question with implicit differentiation. So we're given cotan inverse of x, y equals 1 plus x squared y. We're going to calculate y prime. In other words, we're going to calculate the derivative. Well, cotan inverse, we should start there. Negative 1 over 1 plus xy squared times. The derivative of the inside is the product rule, so 1 times y plus x dy dx equals, derivative of 1 is just 0, 2xy plus x squared dy dx. From here, it's going to be algebra. We have to expand everything, collect the terms, isolate for dy dx. But this is the most important part. The crucial part is getting that derivative correct. Let's go ahead and expand. So in the first term, we're going to get a negative y over 1 plus xy squared plus, well, that'll be negative x over 1 plus xy squared dy dx equals 2xy plus x squared dy dx. Now we move the dy dx's to one side, negative x over 1 plus xy squared dy dx. Subtract x squared dy dx is equal to 2xy plus y over 1 plus xy squared. Now we need to factor out the dy dx. So dy dx, negative x over 1 plus xy squared minus x squared is equal to 2xy plus y over 1 plus xy squared. And finally, we need to write down our dy dx. So dy dx is equal to 2xy plus y over 1 plus xy squared divided by that giant thing, negative x plus xy squared minus x squared. Great job. So one last multiple choice question here. I want you to determine the derivative of arcsine of cos of e to the 4 pi. So go ahead and pause the video, give yourself a chance to try to figure it out. All right, well, let's take a look at each one of these answers. So the derivative of sine inverse we know is 1 over root 1 minus x squared. So all 4 of these seem like to have the initial correct answer. We know the derivative of cos is going to be minus sine, so we're going to have minus sine. These all look good. It's just a question of what happens at the end. We know the derivative of e is going to be e, so we should write this down. And then we know using the chain rule we have to multiply by the derivative of the inside. Oh wait, the derivative of 4 pi, isn't that just 0? There's no x here. In fact, this is a bit of a trick question. The answer for this is not A, or B, or C, or D. It's actually E. The answer is 0. Now I know what you're saying, Mr. Peters, how can you put a multiple choice question without a correct answer? And if you did realize that there was no correct answer, good for you. But this is more to show you something important because likely you started doing a derivative. Likely you started trying to find one of these as your answer when none of them was because the answer was 0. And the reason is because there's no x in this whole function. You need to be aware that no matter how complicated the expression looks on the test or the exam, if there isn't an x, this whole thing is just a constant, and the derivative is 0. For homework, try the questions on page 216, 49 to 63. As well, you can take a look at the inverse trig derivatives worksheet. Inverse trig derivatives worksheet. Thanks for watching.